So the last thing that now you can then do is use each bond to calculate the polarity of an individual bond. Okay, so I'm going to erase my periodic table here because I'll use these middle two as examples. Or sorry, I'll use these two molecules as examples here. We don't need the honk rule right now, so I'm going to erase that. Okay, and I'm going to erase structural formula because we don't need that. Okay, so now what we're trying to do is trying to understand, okay, how can we guess if this molecule is going to be sticky or not? Okay, what we need to do is we need to look at every individual bond and figure out what the characteristics of that bond are. Okay, so for every bond, for each bond, is it polar? Or we can say, is it polar covalent? Covalent? Is it non-polar covalent? I'm just going to shorten that. Or is it ionic? Okay. And this is hard to read. For each bond. Okay, for each bond. And so you have to go through and look at each bond. Let's do that. Okay. Let's start here. Oxygen and carbon. We're going to focus on this bond first. What we have to do is we have to reference the periodic table and look at electronegativity values. So I recommend going back to ptable.com and look for electronegativity values. Electronegativity values. Okay. When you do that, you'll see that oxygen has an electronegativity of roughly like 3.44. And carbon has one of about 2.55. So this bond right here has a difference in electronegativity of this minus that. So, which is about like 0.9. And that makes it a polar covalent bond. Oh, you didn't see that. Okay, I just wrote polar covalent off to the side. Polar. Okay, so since we know that that bond is polar covalent, that means that it's going to have a region of, well, oxygen is more electronegative, so it is going to have a stronger pull on those electrons. So the electrons are going to be more in the region of oxygen. So oxygen is going to have this partial negative charge. This little lowercase Greek delta is used to show partial. And this carbon, meanwhile, will have a partial positive charge. So right off the bat, we've made a dipole. Or we haven't made one, but we just recognize that there is a dipole between those two atoms. Okay, so next, carbon and carbon. Those are the same atom, so they have the same electronegativity value. So this bond right here is going to be non-polar covalent. This one right here, same thing, carbon-carbon, is going to be non-polar covalent. This bond right here, so carbon has an electronegativity of 2.55. Hydrogen has one of 2.2. So 2.2, 2.55. That's a difference of 0.3-ish. So this is actually, if you think back to Professor Dave, his video and where he talks about like kind of the range for electronegativity differences and how you can align that with the bond classification, this bond ends up being also non-polar covalent. Okay, you might say like, oh, well, there's still a difference. So there's still going to be some more negative charge on the carbon. Like a little bit maybe, but in general, this bond is observed as having properties of being pretty much nonpolar. So this is the classification that's given to that bond. So you repeat this process all around the molecule, and it might get a little bit messy. So what you may want to do is just develop a system for writing like NPC, IPC, and then you just write those on the bond as you are modeling your molecule for the day 8 synthesis activity. So I think what you may want to do is label each bond with the bond classification and then write any partial charges that you see because of polarity that is there. And that'll be described in the assignment description. Okay. Just as a quick reminder, the reason why we're doing all this is because we're trying to better understand coronavirus. And coronavirus is made of atoms. And so coronavirus looks something like this or like this. We don't know yet. We'll learn about that on day 9. But we need to understand why different parts of coronavirus or soap, the substances in soap, why those substances may stick to each other or why they may not stick to each other. Okay, and so we need to understand where these little regions of positive and negative charge might be to help us figure that out. Okay, I'll give you a hint. This down here, I left it because this is going to resemble a key component of soap. And so we'll see that tomorrow on day 9. Okay, you may see today if you are looking at something like that in your household products. All right, cool.